Hello, and welcome to this video. In this video, we're going to be looking at electromagnetic induction. So we've seen the ideas of magnetic flux and magnetic flux linkage. We now need to put that into more context as to why it's actually useful. Electromagnetic induction we use literally every day. It's the biggest use of magnetic fields that we'll probably ever have. So we need to be able to understand it. So we're going to start off by going way back to the first video on magnetic fields to remind ourselves of what happens if I have a current in a magnetic field. So what we said was we had a scale and we had a uniform magnetic field. I'm just going to draw it like I'm looking at it. Actually, let's draw it like this. So let's say this is my uniform magnetic field and it's traveling from north on this side to south on this side, and I also had a wire in here, okay, and let's say the current in this wire is traveling this way. Now this was on a scale, and we said that if there's a current therefore traveling inside a magnetic field, I have charges moving in a magnetic field, I must end up with some force that's acting on this. And we said that we could note this force as the quantity F is equal to B times I times L, where B is the magnetic flux density, I is the current, L is the length of wire that's inside the magnetic field. And this is because we have a current flowing. So in this case, we end up with this idea that a current causes a force to act. If I have a moving charge in a magnetic field, it ends up having a force acting on it from the magnetic field. But in physics, most things are symmetrical. We can usually reverse time and the laws of physics should be the same. This is known as time symmetry. Not exactly a brainy term for that. But it means that if I have this idea that I know a current can cause a force, then using this idea of the time symmetry, surely I could play this whole thing in reverse and I could have just a force acting that's going to cause a current. And that is exactly what happens. If we do it the other way around, we end up with something called the dynamo effect. And the dynamo effect is basically how we have functioning generators. So it's the opposite of this idea here. This idea we could formally call the motor effect if we wanted to. These names you don't really need to know. I'm just using them so that we can distinguish the difference between a current causing a force, and in this case we have a force that causes a current. Okay, now if this is going to happen, and we're saying this is the complete opposite, this means that just by having a charged particle inside a magnetic field, a force has to act on that charged particle. That's just based on the fundamental forces that we learned back in particle physics. Electromagnetic force acts on charged particles. If I have a charged particle in a magnetic field, it's going to feel a force. Now what I'm saying for this is the fact that they are opposites means that this motor effect, we said that the complication comes in when we have to introduce this idea of vectors. We said this makes a left-handed system because we used the left-hand rule to decide which direction everything was in. So we said that for the left-hand rule, if I have a force acting upwards, that would be your thumb, right? Because this is going to be FBI. So if there's a magnetic field, that's your first finger, and that means that if you were to line this up, you would end up with a current traveling out of the screen. Okay, so if there was a current traveling towards you, coming out of the screen, and there was a magnetic field line going horizontal in this direction, you'd end up with a force that's pushing upwards. However, if I'm now doing the opposite of this, I can no longer use the left-hand rule, I have to use the right-hand rule. Now the right-hand rule is almost identical. You're still going to use your first three fingers. However, now if you were to put out the left-hand rule and try and copy it with the right-hand rule, you'll find that even though the force and the magnetic field lines are in the same direction, the current is now in an opposite direction. Okay, so I end up with this idea that if I have force going up and I have magnetic field going this way, then I end up with the current going into the screen. And I'll let you line it up to your for yourselves to show that this is true. And this is effectively electromagnetic induction. Now, this obviously isn't the best way to describe it, but this is the very basic idea of how this works. Now we have to say, okay, surely if the thing we had to do in order to induce a force in the first one, which was move the charges, right? We had to change something about these charges. We had to move them in order for a force to be felt. If we just had a lone charge in this area, if we, for example, turn the current off, we no longer feel a force, right? So if we don't have motion, therefore we don't have a force. Therefore, in the second case, something needs to change in order for a force to actually act on these charges. Now, obviously, we can't just have motion of these charges because that means we'd already have a current. So something else needs to change in order for us to get a force acting in order to induce some sort of current in this wire, which therefore induces the electricity. It produces some sort of EMF. And this is where we're going to go back to this idea of the flux and the flux linkage. And we're now going to define a new law called Faraday's law. So Faraday's law is kind of like a heaven-sent gift to electromagnetic induction. Whenever you think about anything related to electromagnetic induction, you always want to first go to the Faraday's law. And Faraday's law says that an EMF, so going back to electricity, this is an electromotive force. We're basically saying electricity is induced by a change in the flux linkage. Okay, we could also rewrite this and say that the EMF, so this would be version 1, version 2 would be the EMF induced is equal to the rate of change of flux linkage. Okay, so now we have an idea what has to change, and what has to change is the amount of the magnetic field that's actually traveling through this surface, or through this wire, or through this coil, because most of the time we do need a coil because we need a larger surface. Okay, now what we've said before is that we have flux linkage, which I'm going to write in the same way we did last time, which was BAN. I'm going to neglect the cos theta for now. I'm going to assume in this case that theta is equal to 0, in which case we just have the maximum flux linkage. I can then therefore say that I know that I can't really change the number of turns on this coil. If I have a coil and I'm going to induce a EMF in that coil, I'm not going to do it by breaking apart the coil or cutting it halfway, because that's not really going to be an effective way. For all of our cases, we say that the number of turns of the coil will always remain constant. Okay, and this leads to the fact that Faraday's law, as it's written in your formula sheet, is that the EMF is equal to N, because this is a constant, multiplied by the change in the flux divided by the change in time. And this is Faraday's law. This is the most important law that we need for magnetic fields. Now, what we can take from Faraday's law is that this is the change in the flux. And we said that the flux, if I were to just get rid of these two ends, is the magnetic flux density multiplied by the area. If I then want to change the flux, I can only do this by either changing the magnitude of the flux density or by changing the area through which the magnetic field can actually travel. So from here we need to then investigate both of these options and see what they both look like. How can I physically change the magnetic flux density? How can I physically change the cross-sectional area of the surface that the magnetic field is traveling through? First, I'm going to say, how do I change the magnetic flux density? Now, in order to change the magnetic flux density, I'm going to leave the law here. I need something that has a variable magnetic flux density. I can't end up with the same kind of uniform field, because if I end up with a uniform field, I obviously can't change the magnetic flux without just turning it off and back on again, right? So I'm now going to have to turn back to our original idea, which was a bar magnet. So if I have a bar magnet, we said that the flux lines, let me say this is north and this is south, the flux lines here look like this, and we know that the density of these flux lines is going to represent the magnetic flux density, right? This is the strength of the magnetic field, where they always travel from north to south, so there should always be arrows on these. Now the idea is, if I then had a coil of wire, for example, so I'm going to have this coil here with n turns, if I were to move it closer here, the cross-sectional area is always going to be the same because it's going through the same coil, but the closer it gets to this magnet here, the lines are closer together, so you're going to end up with a much stronger field, whereas if you're very far away, it means that you're going to end up with quite a weak field. And this is how we do this. So we're basically just going to have this repeating motion of moving the magnet back and forth or in and out of this coil, because that then means that I'm maintaining a constant cross-sectional area while I am changing the magnitude of the flux, I'm changing the magnitude of the flux density that is traveling through this surface. Therefore, I can say, in order to increase the EMF, so I'm just going to move the magnet back and forth, and this leads to a change in B with a constant A, with a constant area. Okay, now by doing this, I then have an induced EMF. In order to make the EMF as large as possible, in order to make this as efficient as possible, so in order to increase the EMF, let me just simplify this now to epsilon. The first thing I can do is have a stronger bar magnet. The stronger the bar magnet is, the bigger the difference between the magnetic field strength when it's further away and closer together. Because if you remember back, we haven't formally defined this for magnetic fields, but it is also true that the rate of change of potential, or not the rate of change, but the potential gradient, so how quickly the potential changes per meter or per unit distance of an electric field and a gravitational field, is a representation of its field strength. The same applies for magnetic fields, even though we haven't defined potentials or anything for it. So the first thing I can do is have a stronger bar magnet. So a stronger magnet. Now the second thing I can do is, this is a rate of change, right? I have this divided by delta t here. Therefore, if I do this much quicker, I have a much quicker change in the flux. I end up with a much larger value of epsilon. So I can move the magnet much quicker. And the third thing I can do in this situation is I also know that epsilon is proportional to the number of turns. So if I increase the number of turns on this coil, say I had 1, I'm obviously not going to get as big of a change of the flux linkage as if I have 1,000 turns. So I increase the number of turns on the coil. So I increase n. And this just gives me my idea of the EMF that I've induced and how I can make it as big as possible. While this kind of idea is fairly straightforward, it's not very useful because this does take quite a lot of energy to actually set up. It's not the best idea. And what you know already from generators from GCSE is that most things work by turning a turbine. And by turning a turbine, we can't necessarily change the magnetic flux density. If we were to just put this inside here and spin it round, it's not really going to change the flux density because this will have spherical symmetry, so everywhere will always have the same flux. Therefore, we have to say that this spinning coil has to be the second way that we can change the flux. So if we move on from this, we then say that our second option is to change A. So if we now look at changing A, this is a much more common example, and this is having a spinning coil in a uniform magnetic field. Okay, so I'm going to draw out a familiar diagram, and I'm going to say that if I were to have a uniform magnetic field here with a strength B, it has to be uniform because now I'm just changing the cross-sectional area. And I'm going to go back to this idea of having a square coil, similar to what happened in the flux linkage video. And we said that this was a square with a cross-sectional area A, or maximum was A naught, which we said is now A squared because it's obviously a square. And we said that I'm going to rotate this around here, and that changes the area, which changes the flux density, right? Or at least it changes the amount of flux. And therefore, if I just say that this is going to be circular, I could do the same thing. Okay, it doesn't really matter if I have a circular coil or I have a square coil, hexagonal coil, as long as the area, as long as it's rotating around a symmetrical axis, so in this case it would be either this axis or this axis, you would end up with the same result. So what we said in that video was that I could define flux linkage in this case as being phi n is the same as BAN cos theta. Okay, where we said that theta is going to be the angle which I've rotated it around. Now, what we're saying in this video is actually that the EMF here is n times the change in phi, okay, divided by the change in t. Now, both of these are on your formula sheet, but this means that if I'm now changing it with respect to time, not with respect to the angle, I now have to change this idea of theta. I now have to redefine what theta actually is, and I have to say after some time period it will have rotated by this amount. Okay, so now I'm going to redefine that graph that we drew before, and instead of having, so this is still going to be A on the y-axis, but now, like I say, I have a rate. I want to know the time variation of how it changes, not the angle. So I'm going to assume that it rotates with a constant frequency or a constant angular velocity, and that means that I can then relate this to time. I assume, so let me write it here, assume there is a constant angular frequency omega. Okay, now that means that I have to now go back to circular motion for a minute, and in circular motion we said that if, or even simple harmonic motion, if we have a cosine of a time, we have to introduce this extra factor in order to make the units dimensionless. So I now have to rewrite this, and you can prove this for yourself if you wish, as cos of omega t. So A is now equal to A cos of omega t. Now I can rewrite this out in terms of the EMF and say that the EMF is therefore just N, and it's just going to be the change in flux. So the change in flux is just the change in B A cos omega t with respect to time. Now, the mathsy people among you might have already noticed that this is just a differential. This is just a differential with respect to time because I can easily replace these with a d. And now, at this point, in order to come up with a second expression for the EMF of a rotating coil, I can just differentiate this expression with respect to time. So I know that B is constant, so I can already pull this out. I know that A is constant because that's just the maximum. So all I'm doing at this point is now I have the EMF is just B times A times N times the differential of cos, actually let me write it as d by dt of cos of omega t. Now, for those of you who aren't doing maths and can't do differentiating, you don't have to worry, you don't have to know how to differentiate, because the formula that you get from this is already on your formula sheet. I'm just doing this to try and prove to you where it comes from, and that you can do this. And actually, those of you who are doing maths should know that if you take the differential of a cosine, it will turn into a negative sign. And this omega has to come out to the front. Now I'm going to neglect the negative in this case purely because it's an EMF, and we'll look at the fact that this is going to be alternating, so it's going to constantly switch between being positive and negative. So what we're finding is just the magnitude of the EMF, but it ends up being that the magnitude of the EMF in a spinning coil is BAN times omega times sine of omega t. And this is on your formula sheet. Now, this we can split into two things, the same way we did when we looked at simple harmonic motion. We said that the number out the front, so in this case, BAN times omega, is just the amplitude. So this means that the maximum the EMF can possibly be is just the magnetic flux density multiplied by the maximum area that it can go through, multiplied by the number of turns in the coil, multiplied by the frequency that it's being rotated around. Therefore, we can also go back to these ideas of how can I actually increase the EMF in this case. And in order to increase the EMF here, I know the EMF is proportional to B. So in order to increase epsilon, I can have a stronger magnet again, because if I have a stronger magnet, I'm therefore increasing the magnetic flux density. I can increase the cross-sectional area of the coil. So if I have a larger coil, I will end up with a larger EMF. So I can increase A. I can have more turns on the coil, so I can increase N on coil. And I can also, in this case, increase the speed that I'm rotating it. Okay, so I increase the speed of rotation. And changing these four things will lead to a larger EMF that's induced. And this is then everything that you need to know about an induced EMF. If we have a change, so the most important thing to take away from this video is this formula here, that if I have a change in the flux, I end up with some EMF. Now what I'm going to say as like a little hint, the way I like to think about it, it's not always obvious if you're going to have a change in B or a change in A. If something crosses the flux line, so if a conductor crosses the field lines, whether that's by rotating through a field line, so it cuts across a field line, or whether it's just passing across, so it's not rotating, it's just moving across the field lines, an EMF is always induced. Okay, and that's because if you're moving across a flux line, you're definitely changing either B or A. Okay, there's no other way to move across a flux line than to change B or A. Therefore, we can say that if a conductor crosses a field line, it will have an induced EMF. And this is how we generate electricity. Most important thing to take away from this video is Faraday's law. And thank you for watching.